Welcome back, students. We'll continue discussion on electric field lines that we had yesterday. Yesterday we talked about how to represent the influence a charge has in the space around itself. The influence a charge has in the space around itself is called as electric field, and electric field lines is a way in which you would represent this influence pictorially. And we also said that there are four characteristics for those electric field lines, and one is that they will start from the positive charge and end at the negative charge, or like they can start at infinity and end at infinity. We've discussed that in detail yesterday. I'm sure you understand what I mean by that. And secondly, we said the electric field lines cannot cross, meaning that if the electric field lines cross, then what you're basically saying is that at this particular point where the electric field lines cross, there are basically two directions in which the influence will act, the force will act. But that is not true. If any charged particle is kept in a particular point in space, then it can move in only one direction. So this crossing of field lines is not allowed. So we saw that too. And then we also saw that the electric field lines will be continuous in a charge-free region. Okay, so these are the main ideas of the electric field lines, basically. And it's like now you can think of them as a stream of rays coming from the charge, right? Okay. So for example, like if I have a charge here, then there will be a stream of rays coming from there. Just like the analogy that I gave you was that of a bulb, a light bulb. Then you can draw lines from the bulb, the lines of light coming from the bulb. So it's something similar, just that you cannot see these lines. Okay? And they are imaginary lines that you are drawing to represent the electric field. Okay. So if I have a charge Q, then I can think of these electric field lines as a collection of lines, rays coming from the charge. It's like this. Okay, so it's a stream of light like that. So I've taken a single charge and then I'm drawing it this way. Okay, fine. And how many lines would you draw? It's completely up to you. Are you going to draw 5 lines, 10 lines, 50 lines? It's totally up to you. But by looking at this picture, you will know that the relative field strength can be found from the density of the electric field lines in that area. For example, like if the field lines are clustered in an area, then you can say that the field strength is more in that area. And if the electric field lines are not that clustered, it's spread out, then you can say that the electric field strength is going to be less in that area. So these are the things that we discussed yesterday, and then we are going to develop the idea of electric flux, okay, from this. What we are going to talk about now is electric flux. So one way of looking at flux is this, like light flux. Okay, it's a collection of rays, right? So one way to look at it is this. If I were to go ahead and then say the electric flux is nothing but the number of lines that you would draw, then that should make sense, right? For example, if we have 50 lines from here, then that's 50 lines. That's the flux. I mean, I'm giving you a crude idea of what it is. You may say, like, somebody is going to draw 5 lines. Well, for the same charge, then I can say, fine, the 5 lines are his flux. Okay, and if you have drawn it as 50 lines, okay, the number 50, that's your flux value. Okay, I mean, it's not, of course, like it's not a constant number, but I think you can get the idea. So from a charge, you draw a certain number of lines. Okay, And this number of lines that you've drawn is the flux. Okay? Keep it that way. It's a crude way of understanding what I'm going to talk about, but then we'll refine it as we go along. So if I take a charge and if I'm going to draw say 50 lines from the charge, then 50 is the amount of flux that is coming out of the charge. Somebody else may draw just 5 lines for the same charge, but let's ignore that for the time being. But notice here, the 50 lines, whether I'm going to take, for example, this sphere, this sphere, okay, or this sphere here, same 50, right? If you take this sphere, how many lines are coming out of this sphere? 50, if I draw 50 lines here. Okay. And then how many lines are coming out of the bigger sphere? Again 50. Okay, and then how many lines will be coming out of, maybe if we draw a bigger sphere? 50, right? For my picture. Somebody else may have drawn it with 5 lines, but that's okay. But I think you basically understand the idea that electric flux is kind of the number of lines which are coming out of this charge. Okay, so that's the crude and basic understanding of electric flux. Okay. So I want you to understand the progress that we have made so far. So what did we say first? We said that if there is a charge, there would be an influence of the charge in the space around itself. That is point 1. And then how do you represent that influence? By drawing electric field lines. Okay, that's electric field lines, and then those lines will have some properties. We saw that. Okay, well, what's the third idea? Electric flux. And what is a flux? Well, the electric flux is nothing but the number of lines that you're going to draw. Okay, so that is the thing. Keep that in mind. Let's see. So if this is the definition that I'm going to have, this crude understanding of electric flux that I'm going to have, let's define it. Okay, let's assign a formula or a mathematical equation to that, and then let's see like how we can actually manipulate it. Let's see. Okay, the idea is this. I'll start from the Gauss law, and from there I'll take it. But I'm not going to call it as Gauss law now. We'll come to that a little later. Okay. First, I said if I were to draw the number of lines, I may draw 50 lines. And if you choose to draw, then you may draw, say, 10 lines. And if somebody else chooses to draw these lines, may come up with 100 lines. Then how do we standardize it? We need some number, right? That's the best thing that we can then do, to standardize the number. And that number could be used by everybody. How do you standardize this number? Well, one way of looking at it is this. For example, this is the charge, right? The Q. What would be electric field at some distance r from the charge? So the electric field E is going to be equal to K Q by r squared. Maybe at this point, at a distance r, and K Q by r squared. Okay, well, and I'm going to use this. I'm going to use this idea now. Let's see. Now, what is constant in this? Well, K is a constant, obviously, and then Q is also a constant, right? So, is it possible it depends on the charge, right? Like if I have 1 coulomb, then this is 1. If I have 10 coulombs, then it is going to be 10. If I have 100 coulombs, it's going to be 100. But once I have this charge, once I have 100 coulomb charge here, it's too high, but I'm just giving you a number. If I have 100 coulomb charge here, then this would be a constant number. This would be the same for me, and for you, and for anybody else who's trying to do this stuff, right? So this is constant. then I can move all the other things now. So E r squared by, say, constants of k. Okay. Let's say k is going to be q, right? Note that now it doesn't, I've got a constant here. Now it's a constant, notice it. This E can be varying, this R can be varying, because like here I have one R and then one E. Maybe here I'll have a different R and a different E. But this won't change for either case. So I have kind of incorporated the idea that he was talking about before. What was the idea? I draw a number of lines, 50 lines. And if I take this sphere, this small sphere, how many lines will be coming out from the charge? 50. And if you take a bigger sphere, how many lines will be coming out of that sphere? 50. You see, I've got a constant number now. Right? Similarly, I'm getting the same constancy here. It doesn't depend on E, it doesn't depend on R now, but then it depends only on the charge inside. So I can use this charge Q itself as the amount of flux coming out. Okay? So this is the idea I'll take. But then I'm going to refine it further. Okay? It's not just going to be Q, but I'm going to refine it a little further. But I think you can get the idea. So Q would be the part of that constant that I'm going to use, surely. Okay? So once I get this, whether it's me who is doing the calculation or you who is doing the calculation, or somebody else doing the calculation, then this must be right. This is a constant number now. Okay. Fine. So if you understand it, then we will refine it a little more. The idea a little more. Okay. Let's take this. Let's say, I'll take, this is the, for this charge, we talked about a sphere covering it, right? But now I'm not going to take the entire sphere. I'm going to take just this area. Let's say I have a charge here, and this area is actually part of the bigger sphere. Okay? Imagine a bigger sphere. This is a charge. This is a charge, and at this distance, draw a sphere. Now the number of lines, the total number of lines will be coming out would be a constant, which will have something to do with Q now. Okay? But think about it. Look at this. This is part of the sphere. It's a bigger sphere. This area is basically part of the sphere. So how many lines will go through this one, this area? How many lines will go through this one? Because, coming back to our example, if I draw 50 lines will go through the entire sphere. But now I got only this area. It's not the entire sphere now, right? At this distance. It's not the entire sphere. So how many lines will go through this one? Certainly not 50. Maybe some other number. Correct? So that is what we are going to see now. Okay, so I have this, let's say like I have this area. Imagine that I kept my phone like this, so there will be a certain number of lines that will go in there. Okay. So if I take this area, note here, there are only 2 lines going here. But if I take the same area and bring it closer, clearly, so 4 lines will be going. I hope this idea, I think, well, we discussed yesterday. So this area 2. The area is farther, then less number of rays go through, but the area is the same area. When you bring it closer, then 4 lines go through the area. So notice that the number of lines going through this area depends also on how close or farther it is. If it is at this distance, maybe 2 lines go through it. And if you bring it closer, then 4 lines will go through it. Okay? So I can say that if I come back to this equation, if we come back to the same equation, E is equal to k by r squared. So depending on r, okay, the E value will change, correct? Okay, that's the thing. If I'm farther, then the E value is reduced. And if I'm closer, then the E value will be greater, but then R will reduce. Are you okay with that? I hope you understand this idea now. Okay. And not only that, the second point is, see, if I keep this like that, okay, then there are two lines going through this, right? Let's say. If I keep it like this, there are two lines which go through it. The same area. See, but if I keep it like this, notice here there's only one line going through it now. Okay, like a stream. Imagine that like there is a stream of water coming here and then hitting this. If this is perpendicular to the flow, then all the water will go through this area, right? But then if I turn it like this, you see the amount of water that will go through this will be smaller, right? Like this, like a mirror, let's say. Let's say this is light. This is light. This is light. Okay? So if I keep the mirror like this, then all these lines will go through the glass, will go through it, will fall on the mirror glass. Okay? But if I turn it, let's say turn it, if I turn it like this, notice. Okay? You see, for the same length, if I turn it like this, now your mirror or the glass is like that. You see, this goes through it, this goes through it, this goes through it, and maybe this is going, it's not going through it now. Okay? So there are three lines go through this. So there are two things that are important here. Okay? If you want to find the number of lines that go through this area, it is not just the area alone that I have to be considering. I also have to see how this area is oriented to the flow. Okay, if it is perpendicular to the flow now, then all the lines, the entire area will contribute to it. But then if it is tilted in any way, then the entire thing is not going to be used there. Okay, so I can say that the number of lines that go through will depend on the area too. Right? Okay. So if you understand this idea, the area and also the orientation of the area. So now I will come back to this. Here, what I'm going to do, I'm going to manipulate it a little bit. I'm going to say E is there. And then what is this R squared by K? I'm going to make some changes to that. What I'm going to do is this. I'm going to do this. E and then 4, E R squared is there, into, I'm going to multiply it by 4 pi and divide this by 4 pi. Well, okay, so the value will not change, right? So that's going to be Q. Okay? So what is it going to give you? So this is actually the surface area. The surface area of the entire cylinder, an entire sphere. Look at this distance R, an entire surface area can be taken as 4 pi R squared, right? So I'll say E S is equal to K into 4 pi. And that is equal to Q. But what is K? K is actually 1 by 4 pi epsilon naught, right? So ES is equal to 1 by 4 pi epsilon naught into 4 pi. It's equal to Q. Right? So this and this will cancel. kind of, and then so what will happen to this? So this will go up, so this will give me E epsilon naught S is equal to Q. So I can say that E into S is equal to Q by epsilon naught. So what have we got here? Electric field intensity E and the surface area of the sphere. If you multiply both of them, then it's going to give me Q by epsilon naught. Okay. So this is idea we are going to use here. Okay. And we also said like this is E into S. But note here, this surface is perpendicular to this line at every point, rather like it's here. It's like this, it's like this, it's like this. 90 degrees to line because it's going through the radius of the sphere. Okay, so if I were to mathematically represent this, then I would say that flux, electric flux, delta phi is equal to E vector dot delta S vector. So delta S is that small area. I'm not taking the entire area. Delta S. Okay. And now I note here I've also taken care of the orientation here. E dot delta S. So which means that if you assign a vector, if you take this area as a vector, then if I do a dot product of that vector with this E, then I'm going to get some number delta phi. Okay, so that is how I define it. So this is going to, but how we define delta S now? How can we define delta S? Well, that is going to have this will have a magnitude delta S, alright. It's going to be the magnitude. Okay, maybe if it is like this is 15 and then if it is 10, or if it's 20 and 10, it's going to be 200 centimeters square. So that's the delta S. 200 centimeters square is the delta S for it. But what about the direction? What do you mean by that? Okay, how can an area have direction? Well, the area does not have a direction, but I'm going to assign a vector to it. Okay, I'm going to consider that as a vector. Okay, it's a pseudo vector I'm talking about now. Okay, there is no natural vector assigned to that area, but I'm going to assign a vector to that area. Okay, and I'm going to say this vector is perpendicular. The area vector is perpendicular to the area. So this is a vector for that area. Okay. So now notice here, if this is it, if this is area, like I'm keeping it like this. Okay. If this is area here, and then the vector is going to be in this direction, normal to the area. If it is normal to the area, then I can use a dot product. I've got two of them. So now this is going to be something like delta S into this N. That's area. Okay. So now this will give you, so then delta phi, the flux through this area is going to be equal to E delta S and then cos theta. Where theta is the angle between the E vector. At this point you will have an E vector, right? This is the direction E vector. And then at this point, suppose if this is the vector here, okay, is a delta S vector, right? Because it's like this, it's perpendicular to that. So then there would be an angle between that and this. So that is the angle between the two vectors. So this is the area vector, the delta S vector, and this is the E vector. E vector is like that along the line, along the electric field line. And this would be, delta S would be in this direction. Okay, this would be in this direction. So notice that there would be an angle between the two vectors. And if I do a cos theta of it, then it will give me the amount of lines which go through it. Because it will going to give me only that part of the area which will allow the electric field lines to go through. Okay. Let me try to explain it a little more. Think about it this way. focusing. You see, let's say this is the direction of the flow, okay, and let's say your area is something like this. I've kept the area, the mirror like this. So there are lines like this, there are lines like this, and there are lines like this, and there are lines like this. Okay? So this is it. So only 4 lines go through this. Okay? But it is like, note here, it is like this distance, right? Like this distance. The entire area is not participating in it. Like if the entire area wasn't participating in it, then you will have 5, right? Like if it is 90 degrees here, then you will have all the 5 lines going to go through it. But then like now, it's not entire area participating. Like it's like there is a slight tilt. So which means that you are going to have the vector of this area like that. So that is the n vector of the area. Yes, area vector. It's like now it's tilted. Okay. Which means that only this area is available, only this area is available for the lines to flow through. It's like that. Not the entire thing. Not the entire thing. Okay? It's like this. So only, this one. This area is available for the lines to flow through. I hope you understand what I'm saying. If that is the case, then how do I calculate this area? This is A, this is the total, this is A, the entire area. And what would this be? I need this one, right? I need this one. So then what is the angle between these two things now? So this is the angle, right? I need to find this angle. Okay, so if this is theta between them, and this is going to be theta, this angle is going to be theta, so you require A cos theta for this. So this would be simply A cos theta. So that is the effective area available for you. Not the entire area, but the effective area is only this. Okay, it's only A cos theta. So that is what I have tried to incorporate here. So it is not the entire delta is, but the delta S cos theta is what is involved in this. So that is why you require a dot product. When a dot product A dot B gives you AB cos theta. Okay. So, but to use a vector dot product, you require a vector. But area is not a vector. So you are considering that as a vector. It's a pseudo vector. It's not actually a vector. But to accommodate this aspect, you are treating the area as a vector when it is not actually a vector. Okay? So if you want to find, so the simple, even if you do not understand all that I have talked about so far, understand this. If there is an area and if there is flux flowing through it, then if you want to find the amount of flux which is flowing through that area, then what you need to do is this. The amount of flux going through that area will depend on orientation of that area to the flux, right? Okay. If it is like this, then more will go. But if it is like this, less will go. And if it is like this, then nothing, all the lines will graze through this, just graze through this, the area, but nothing will go through the area, right? If I keep it like that, if I keep the phone like this, which line is going through that area? No line. No flux goes through it. But if I do it like this, some flux go through it. And if I do it like this, a lot of flux go through it. This is a maximum. And this is like, it's reducing. And the moment I bring it here, then no flux goes through it. The flux just grazes through it, but not, grazes over it, but then not through it. Okay? So you understand that, and if you want to find amount of flux, then this is the equation I will be using. So delta phi is equal to scalar quantity, because we need a number, right? Just 50, 100 or whatever we talked about. Delta phi is equal to E dot delta S. This is a small area and it's a vector assigned to the area. And how is the vector? The vector is perpendicular to the area. So if this is area, this is the area vector. So the area turns and the vector turns. Notice here, turns, vector turns here. Okay. So when it is like this, you see it is making 180 degrees with the incoming flow. Or if it is flowing like that, then it is making 0 degrees with the flow. Okay. But now it's making some angle, then effectively reduces the amount of flux which is going to go through it. And then when it is like this and is like that, then note here, nothing flows through it. And if I take this as a vector and the flow is like that, then it's the angle between this vector and then the flow is 90 degrees. So cos 90 is 0, so no flux will go through this area. So that is the idea of this. Okay, I want you to understand this, and let me summarize that again. Even if you have not understood anything that I have discussed so far, understand this. Flux is nothing but a number that you assign to the amount of electric field lines which come out of that charge. Okay, and as I said, like if you draw that picture, you may draw it with 50 lines and I may draw it with 10 lines or whatever. Okay, how to standardize that? You need to come up with some way of standardizing it, not through a picture but through mathematics. So the way to do that would be from here. So like if I take Q itself as a measure of the amount of flux coming out of the charge, then I'm kind of safe here, right? Okay, like I can kind of implement it, but then I cannot just implement it straight away. So the way I'm going to do it is this. I know that if I have an area and if flux is coming through it, then if I keep it perpendicular to the flow, meaning that the area vector will be 0, will make 0 or 180 degrees to the flow. Assume that if we keep this perpendicular to the flow, then all of the area would be utilized. Okay, and maximum flux will go through. Okay. And then if I tilt it, then the amount of flux which is going through that area will be less. And if I tilt it like this, no flux will go through it. And it will only graze over the area, surface of the area. So to implement it mathematically, to represent this mathematically, I have this expression. So delta phi is equal to E, that's electric field strength at that point, dot delta S, which is the area vector. So this is the flux. Delta phi is equal to E dot delta S is the flux which is going through that small area. Okay. This is the idea I want you to understand. Okay. Note that area in itself is not a vector, but you are manipulating it, you are assigning a vector-like quantity characteristic to it actually, and you convert that into a vector quantity. Area is basically a scalar quantity which you are converting into a pseudo vector quantity. Okay. To use vector algebra. Okay. So once I make it as a vector, notice here all that you need to know is the angle between these two. Now you see E dot delta S is A dot B. The scalar product of the vectors can be used. That mathematics can be used in this case. And that is the only reason why I am converting a scalar quantity into a vector quantity, even though it is not a vector quantity. Okay? Keep this equation in mind. Okay, let's summarize this. So you have a charge, and then let's suppose that there is a number of flux which is coming out of the charge, like this. There's a number of charge coming out of this. Like if I imagine a sphere around it, and the total number of charge coming out of it would be this number, like whatever number they calculate. Okay. If we draw it with 50, then it's 50, if we draw it with 10, something like that. Okay. So now what I'm trying to find is this. Let's take this. Let me talk about the entire thing. So E into this S meaning the surface area of the entire sphere is equal to Q by epsilon naught. So this would be a constant, right? Q by epsilon naught would be a constant. Absolutely. Why? Because epsilon naught is a constant anyway. And then Q is the amount of charge you have here. Right? If you have 1 coulomb, then 1 by epsilon naught. Whether it's a smaller sphere or a bigger sphere, you will have the same thing, Q by epsilon naught. Right? Okay. Now, how do I get this first of all? How do I get, I'll call this as entire flux phi. The entire flux phi is equal to E into the E at this point maybe, and then the entire surface area of the sphere. If we multiply that, I'm going to get Q by epsilon naught. It doesn't depend on what your E values, it doesn't depend on what your S values, but all you know is E and S will adjust themselves such that their product will always be equal to Q by epsilon naught for the charge. If we take the entire surface, that's the total number of flux coming out of it. Okay. So at the same time, we also said if we take a small area, maybe like this is like that, a small area at this length, okay, this kind of surface area. I mean, I'm drawing only one line, but it's not one line. It's actually, I mean, I think you imagine this kind of an area. It's not a complete sphere, but this kind of a sphere. But when you look at it like this, then you are going to see only this line, right? So that's the line I have drawn here. Okay, this will have a delta S. Okay, a very small area. So delta S, and I'm also going to assign a vector to that. Okay, and at this point, you are going to have an E there. So the delta phi. What is delta phi? Delta phi is the amount of flux going through the area delta S. Delta phi is the amount of flux which is going through the area delta S. So delta phi is going to be given by the expression E dot delta S vector now. Okay. Well, obviously this is not going to be equal to Q by epsilon naught. Why? Q by epsilon naught is for the entire sphere. But this is just delta phi. If this is 50, this can be 2 or 3. So this is a very small number. Then how do I go from here to here? What should I do? I should take this delta phi and the delta S, and then I also should take another delta S here. Maybe it's delta S1. If what is the flux coming out of this? I call this for delta phi 1. Then this is equal to E dot delta S1, and I will take another, this is delta, I call it as delta S1, and then delta S2, and then there will be some flux which will come out of this surface, and there will be some other flux which will come out of this surface, which is delta S3, and then there will be another surface here, and delta S4, something like that, right? You have many different small surfaces. So if you calculate the flux through this, and then flux through this, and then the flux through this, and then the flux through this, flux through this, and flux through this, if you calculate for all the small areas comprising that sphere, then if you add it all up, then I should be able to get this, right? Q by epsilon naught. So this delta phi is equal to E dot delta S. That's the amount of flux through that small area delta S. And then delta phi 1, and delta phi 2, and delta phi 3, and delta phi 4, delta phi 5, all that you will have. Okay, I'm just divvying it up, I'm dividing this area up into many small, the entire surface area into many small areas. And I'm trying to find flux through each area. So what would be my final flux be? If you want phi, then what would that be? If you want phi, and what I'm going to get now, that will be equal to delta phi 1 plus delta phi 2 plus delta phi 3 all the way to delta phi n. Right? Okay, so that is going to give me this. what would that be? So this is going to give me, for example, like this would be E1 dot delta S1 plus E2 dot delta S2 plus E3 dot delta S3 all the way up to En dot delta Sn. Okay, makes sense. So now what is my phi? This phi is going to be equal to, again, we're going to use a symbol that we discussed in the class, the sigma symbol. So I'm going to write this as sigma Ei, or I going from 1 to n, Ei dot delta Si. So that this may look fancy, but it's a very simple idea. What does it mean? I'm going to calculate the flux through small areas and add them all up, and if I add them all up, and I'm going to find the amount of flux from the charge, the total amount of flux from the charge, and which is going to be equal to q by epsilon naught anyway. That's what we've done. That's a number we come up with, right? That's a method which will standardize the amount of flux. What did we say? Amount of flux is the number of lines coming out, okay, from the charge or going into the charge if it is negative. But if I were to draw the picture, I would draw that with 50 lines, and if you were to draw the picture, you will draw it with maybe 500 lines or something. So there is no uniformity in the way that we are going to draw those lines. Then how do you bring uniformity? Well, if I take this number, q by epsilon naught, that's a constant number for the charge. So that would be the same for you and me and everybody else. So I'm going to treat this as the flux. If I treat this as the flux, how do I get to this? Well, I'm going to find flux through small areas and add them all up. Then I will get the amount of flux coming out of the charge. In our case, it is q by epsilon naught. So that is what we have done here. So even though it looks a little complicated and fancy, rather intimidating, these symbols, they basically mean very simple thing. The sum of flux in different areas will give you the total amount of flux coming. Very simple idea. That's what it is. Okay? So now, what would be, now that we defined this unit, this quantity, flux, okay, what would be the unit for this? Very easy, right? So Q, phi, the amount of flux is equal to, okay, what is that? I mean, simply ES, and also is equal to Q by epsilon naught. So you have two ways of doing it. You can take Q coulomb and then epsilon naught unit. That's one way of doing it. It's going to be a little complicated. But then you can simply take this ES. You can use the units of these two things to come up with the unit for flux. So the unit for electric flux is equal to, what is the unit for E? That is Newton per coulomb. Right? The amount of force per unit charge. Newton per coulomb. And what is S? Surface area. That is simply meter square. Okay? So the unit for electric flux is this. Okay, I will write it as Newton meter square per coulomb. And if I were to use the unit for the charge and then epsilon naught, then I'm going to end up with the same. Hope this makes sense to you. So we have talked about electric flux also. I want you to think about all this. I want you to think about what we have done so far. We talked about charges, and then we talked about the Coulomb force of attraction and repulsion between them. And then we developed the idea of a field, and from the field, to represent the field, we developed the idea of electric field lines, and from the electric field lines, we have developed the concept of electric flux. So there is a logical flow in all that we have done so far. We got from step 1 to step 5 logically. Okay, hope you understand this.